Hi, everyone. Welcome to our presentation today. This is Chen Pan. On behalf of our team, I'm glad to present to you our work, Aperiodic task scheduling of energy harvesting embedded systems to you. The first author is Dr. Hongzhi Xu. He received his PhD degree in computer science and engineering from Hunan University, Changsha, China in 2018. He's a professor in the College of Software, Jishou University, Zhangjiajie, China. His research interests include embedded computing system and parallel and distributed systems. So first, I will introduce some background to you. So nowadays, we're in this IoT era, and there's various IoT applications supported by tens of billions of embedded devices. And such number keep increasing every year. However, to power those huge number of embedded devices effectively and efficiently, traditional batteries not good enough, right? Due to the environmental concern and also constantly maintenance effort, to change the battery. So to address this issue, energy harvesting that can harvest and harness energy from ambient natural environment become more appealing, which can enable various applications such as structure integrity of the bridge. You can monitoring that sustainably, right? You harvest the energy from the vibration of the bridge, and also you can do the livestock tracking to help better animal husbandry, and also you can monitoring the wild animals' health and behavior, right, for some scientific study. So, however, despite all those benefits, energy harvesting power is generally weak, which motivates us to develop methods to improve the energy efficiency of embedded systems. So to do that, in this paper, we mainly developed a technique to maximize the quantity of service, while at the same time we use the DVFS to optimize the energy efficiency of the embedded system. So to do that, in particular, we're going to develop an algorithm called energy constraint and the deadline constraint reward maximization algorithm, which is EDCRM for short, to schedule the execution priority for the stochastic task. So to do that, we also designed two sub-algorithms. One is called FindFL, the other is called FindFLSL. So FindFL represents the find frequency level, and FLSL represents the find frequency level and the service level. So because quantity of service really related to service level, right? So we need to do both. So together, they will choose the execution frequency and the service level for stochastic task. And in the end, we will compare the results, which has, show the effective of our algorithm. So this figure actually shows the overview of the system model. The whole system divided into two parts. From the left side is software part. So from the software perspective, each newly arrived aperiodic task will contain the following information, right? So in content A represents the arrival time, D represents the deadline, WSL represents the worst case execution time, as well as the service level it select. It is available for you to select, right? And through the EDF algorithm, which is based on the deadline, right? So based on the deadline, we're gonna find the appropriate position to insert the the newly arrived task in the ready queue, right? So whenever we're done with the software part, we have the ready queue ready, and on the the hardware perspective, so we're gonna harvest the energy from the natural environment, and then those energy will be stored into energy storage, right? So storage, and so after that, the EDCRM, the algorithm we designed, will take the task-based information as long as the available energy which we can capture through the ADC. So when those information together, we'll be able to select the appropriate execution frequency as well as the appropriate service level for the task. So here, each task I, we define the several available service level J. So here we use Xij to represent task I and J's service level, whether it has been selected or not. So if X equal to 1, that means the service level J will be selected. Otherwise, it will not be selected and X will be 0, right? So during the runtime, the task can only be allowed to use one service level for the runtime operation. In this equation, so we define the total reward based on the cumulative service of all tasks under the same amount of energy harvesting environment, right? So our goal eventually will be to maximize the total reward, right? The total reward is our optimization goal. And so to do that for the first task, whenever in the ready queue, right? So for the first task, first things we need to do is to decide, right? To check whether this task has been preempted or not. So if it has been preempted, that means this task has been executed before, right? So if the task has been executed, it has already been selected the service level, right? So we're not gonna talking about the service level selection under these circumstances. Therefore, we're gonna use the FindFL to select the appropriate execution frequency. Then on the other hand, for new tasks, the service, if it has not been selected, then the system will use the FindFLSL to select the proper execution frequency as well as the service level for execution. So both algorithms will take the task-based information, arrival time, deadline, WSL, as well as available energy into consideration to generate the corresponding command for a processor to tune the DVFS into appropriate level, right? I mean, DVFS to tune the frequency into appropriate level. So the key metrics to executing these two sub-algorithms are as follows. So we need to have first parameter is latest finish time, which is LFT for short. The other is the maximum possible energy consumption, which is MEC for short. And so the detailed calculation for these two just showing on the paper, right? We're showing the paper. So for the first we're going to talking about the FindFL design. So the key here is we trying to find the maximum frequency that is allowed to support our current task. So by doing that, the way we're doing that is we want to speed up the performance, right? Want to speed up the performance. However, we need to have a constraint. The constraint here is we need to satisfy whether the latest finish time, if it's smaller than the deadline. So if it's less than the deadline, so that means we can finish before deadline, right? So satisfy that condition first, and then we also need to satisfy whether the energy we required can be offered by the energy storage, right? Available energy right now. So if both conditions satisfied, then we're going to pick up that frequency for execution. Otherwise, we're not going to select any, right? We're not going to select any frequency. So for the FindFLSL design, so it's similar, but our goal right now is like we want to maximize the frequency, the service level, right? So that's our optimization goal. So to do that, we will traverse from the highest frequency, highest service level to the minimal service level. So here, the service level 1 represents the highest service level, right? Quality. It can produce the highest quality of service. And the rest is the frequency, right? So whenever we select a certain service level, then we're gonna traverse through all the frequency level to find out the maximum frequency that is allowable for us to operate based on the LFT and the MEC, right? The condition, right? You should execute it before deadline, and there's enough energy for you to do the execution, right? And if current service level not satisfied, we're gonna downgrade the service level, right? Until the end, right? Until the end. So if there's no service level qualified, then we're gonna return as false. Otherwise, yeah, you just return the frequency level, service level that is the maximum frequency level and maximum service level that is allowed for you to do the execution, so that you can maximize the total reward. Okay, so you can see actually here is like if a current task has been preempted, right? So we're going to go back and execute the FindFL again, right? Whenever you resume the computation. So we also conduct experimental performance evaluation. So from the experiments, we based on the processor X scale, right? The parameter we extracted from this processor, and particularly it has 6 actually have 6 level, and the first level 0 is idle state, and the rest part is a tunable DVFS level. So for each DVFS level, we have a different voltage, different power, different frequency, and also the energy efficiency. So here, energy efficiency is defined as a ratio of execution frequency to the power, which represent the number of cycles executed per the unit of energy. On the right side, we also give the energy harvesting parameters. So this is the power trees we use. So now let's take a look at experimental parameters. So in this experiment, we use improved EDF algorithm as a baseline. And for the improved EDF algorithm, we choose the 5 fixed frequency level, and highest 1000, and we normalize this 1000 megahertz as a 1. So in this pattern, the 0.8 represent the 800 megahertz, 0.4 represent 400 megahertz respectively. So to observe the performance, we generate 500 tasks randomly, and the scheduling result of different algorithms shown in this table. As we can see here, the EDCRM complete all of the tasks, all of 500 tasks. However, for IEDF, at a different frequency level, majority of them cannot finish all the tasks. And further, we also want to observe the robustness of the algorithm under different processor utilization. So here, the higher process utilization means each task will have more workload, and it will probably have not enough time or energy to finish all the tasks. So under this kind of the scenario, we can observe here the the EDCIM actually doesn't affect too much by the process utilization. It still maintained a very stable completion rate as well as a total reward. However, the baseline IEDF, for instance, the worst case is IEDF 0.4. We can see here is the completion rate actually dropped very significantly, and so compared with that, with the 400 megahertz of IEDF, our proposed algorithm have not 29% improvement. And so compare with the total reward, the EDCRM have averagely 40 or even more % improvement compared with the IEDF baseline. Yeah, in particular here, for the IEDF 1.0, we have 53% improvements. So in conclusion, yeah, the stochastic arrival task with the multiple service level to be executed in the energy harvesting embedded system, we propose the EDCRM algorithm to schedule tasks within the deadline and under energy constraints. So we also propose the FindFL and FindFLSL algorithm to determine the service level as well as the execution frequency level of the task. And the simulation results show that the proposed algorithms can significantly improve the system reward compared with the IEDF algorithm. And this is our contact information, and the corresponding author is Dr. Hongzhi Xu. And thank you for your time and patience. If you have any question, please feel free to ask.